Alright, so in this video I'm gonna be explaining another important paper with the title Variance Reducing Couplings for Random Features. These random features of Ali Rahimi and Besht in 2008, more than 100,000 citations shows the importance of this. So this ICLR paper in 2025 is important. Kernel methods suffer from poor scalability. The need to materialize and invert the gram matrix leads to time complexity cubic in the size of dataset. And substantial research has been dedicated to improving scalability by approximating this matrix, a prominent example being random features. So these randomized samplings, these randomized mappings construct low-dimensional or sparse feature vectors that satisfy this. And for variance reduction for random features, we replace E by mean over random samples. That is the Monte Carlo estimate of K. So we define this kernel estimator. The coupling between, so what is coupling? First, what is coupling? The estimator is unbiased, provided each frequency omega sub I obeys some marginal distribution. Independence of omega sub I is not required. Any joint distribution with marginals eta gives an unbiased estimator. We refer to the set of such joint distributions as couplings. The coupling between frequencies determines the estimator variance. So we want to minimize this expectation of the cost function, where our cost function is just this one. And this alpha is just a set of couplings from m random variables with marginal measures eta. And this is precisely the Kontrovich formulation. So we consider the task of approximating the popular Gaussian kernel with data x sub I. So we use again the Ali Rahimi's approach, the random Fourier features with these spaces and these random features. Here we are concatenating m different random features, sine and cosine bases. So changing the basis functions k can be approximated using random Laplace features. Solving the optimal transport problem for maximal variance reduction. There is a lemma that relates these things, that when estimating k with m orthogonal RRF, the optimal transport can be just written as this. And C is a cost function here. So we proposed this random features a computational efficient coupling that is guaranteed to reduce the variance for any m. While an analytic solution to marginal optimal transport variance reduction is for now out of reach, we can make progress using numerical optimal transport solver. Our strategy is to restrict this alpha, the full set of joint distributions over m random variables, with x sub d, with chi, so the marginals, to tractable subset amongst which we can efficiently optimize and sample. One such subset is provided by Gaussian couplings. And then another video I talked about graph random features. We can use the same idea. Coupled random walks. Of course, I've seen these in theoretical spectral graph theory, but they also use it in machine learning here. You see, the center is a bipartite matching between quantiles of geometric distributions over walk length. And the right one is just the ensemble of graph random walks with lengths to be coupled. So this is how we construct graph random features. Psi here is maps from the set of graph random walks to sparse n-dimensional feature vectors. But it satisfies the psi that satisfies this. So they did it for a pair of walkers. They have a estimator. Whenever you see hat, it means it's an estimator. It's not the real one.